welcome to another video. Today we're gonna have a go at making a freefall collision simulation. So what is freefall collision? Well, basically the simulation would be like this. We're gonna have two masses, two balls, I'd say one higher up than the other. This is the center of mass. And these two balls, as you can see, was represented by the different sizes, have different masses. This one has a mass of m1, this one has a mass of m2. And there's a constant force of gravity, so you can say, there's a constant effect of gravity that is both affecting the movement of these two balls. And there would be a ground here, and there would be no loss in kinetic energy by the bounce with the ball, by the collision of the ball with the ground. And so what this means is that if, for example, this mass m2 hits the ground with velocity of v2, it's gonna go up with a velocity of minus v2. And of course here v2, the positive means downwards and the negative means upwards. And so when either object hits the ground, it's gonna go up in the opposite velocity but with the same magnitude. That's the assumption that we're gonna make. But now there's the main I'd say point, the point of making this simulation is seeing what happens when these two masses collide with each other. And so first of all, there's no air resistance. And so we will see that these two balls will follow with the same acceleration, so with the same speed, because they're both going to start with a velocity of 0. And so they're going to fall. M2 will bounce upwards first, and M1 will still be moving downwards. And somewhere over here, there will be our first collision. Our first collision will happen in this point at about this point. And so what would happen in these collisions? And you could imagine that after this first collision, M1 will move slightly upwards, M2 will go downwards again, and then bounce with the ground and go up again. M1 will still be moving. And right about here, there will be our second collision. And third and fourth and so on. There will be if we run the simulation for an infinite amount of time, we're gonna get an infinite amount of collisions, because there's no energy being lost. So and also we're assuming that it's elastic, i.e. the collisions between these two balls are elastic, and so there's no loss in total energy of the system, in the mechanical energy of the system, and so the system will never stop. And so what would happen in these collisions? All right, let's say we're gonna, of course this system is vertical, but it's gonna be no different in it doesn't matter. Let's say we have this situation where ball of m1 with velocity v1 and ball m2 with velocity v2, I say u1 and u2 collided. Collision happens, and what happens is ball m1 moves upwards with v1 after the collision, and ball m2 moves downwards with v2, velocity v2, and still the same mass. How can we formulate this? How can we know m1 and u1. M1 and u1 will be recorded in the system, but we have to know how these values for the velocity changes after the collision. And so what do we know? Well, first of all, we know that linear momentum is conserved, and secondly, we know that total energy, so kinetic energy, is conserved because it's an elastic collision. So I'm just going to erase this. what would happen? What would be our values for v1 and v2? Well, let's write the things that we know down first. We have, first of all, we have conservation of linear momentum. So we have m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now you see that we have two terms. No, we have one term in each side that has m1 and one term in each side that has m2. So for convenience, I'm going to get m1s to one side and m2s to one side and get m1 u1 minus m1 v1 is equal to m2 v2 minus m2 u2. And then I'm going to wrap this with m1 to get u1 minus v1 is equal to m2 of v2 minus u2. That's my first equation. I'm going to label that with a 1. Now we have our second principle, which is conservation of kinetic energy. Kinetic energy before collision is 1/2 m1 u1 squared plus 1/2 m2 u2 squared, and that's going to be equal to 1/2 of m2 v1 squared plus 1/2 m1 v1 squared and plus m2 v2 squared. Now again, we have m1s and m2s. So first of all, we're just going to erase the 1/2. So erase all the halves, multiplying each side by 2, and then we're going to flip them. So we're going to have the terms with m1 in here and m2 in here to get m1 of u1 squared minus this here, so v1 squared. Imagine that being here. And that's going to be equal to m2 of v2 squared minus this goes to here and get u2 squared. Now, and I'm going to label that as equation 2. Now, if we have two equations, we know that we can divide the two equations and still the equality will be there, because after all, it means that this is equal to that and that's equal to that, and so this divided by that is going to be equal to this divided by that, or in the other way around. And so what we're going to do is divide equation 2 by equation 1. Then here we get, in the left side of the equation, we have m1 cancels out, so u1 squared minus v1 squared over u1 minus v1 is equal to this divided by that, m2 cancels out, and so we get v2 squared minus u2 squared over v2 minus u2. Now that here, we could represent u1 squared minus v1 squared as u1 minus v1 plus times u1 plus v1. Basic mathematics. And do the same thing here. We could represent this, we could factorize this into two parts. Now what do we notice here? Here we notice that these two terms are cancelled out, and here we notice that these two terms are cancelled out because they're the same. And so as a result, we get u1 plus v1 is equal to v2 plus u2. Now it all depends on what we're trying to find. We could find a term for both v1 and v2, but let's say we're just going to do v1 first. We're going to get an expression for v1 first. I'm just going to draw our system, what the system we're dealing with here. So we have that here, this here. They're both following. This has a m1, u1, m2, u2, and there's a constant force effect of gravity. Constant effect of gravity, and we have a ground over here. Alright, so in order to get v1, first we have to eliminate the term v2. And we have a term here that relates v1 and v2 with all those constants. Remember that u1 and u2, we know what their values are. And so they're they can be considered as constants, as so is m1 and m2. m1, m2, u1, u2 are all constants, whereas v1, v2 are the terms that we were trying to find out. And so here we could say that v2 is equal to, when we get u2 to this side, we have u1 minus u2 plus v1. We can say that v2 is equal to u1 minus u2 plus v1. And so we have represented v2 in terms of v1 and other constants. And let's look at the simplest equation that we could find. And that is this equation over here. Equation 1 is much simpler than equation 2. So we're going to input this here into equation 1. So we have, in the left side, it's same, but I'm just going to expand it because we're going to have to rearrange it and see what terms cancel out. And so this here, we're just going to expand it and write it down as it is. So we have m1 u1 minus m1 v1. That's our left side of the equation. And the right side of the equation, we have m2 times, and remember that we're going to expand this also. We have v2, which is u1 minus u2 plus v1 minus u2. And so we have minus u2 and minus u2. And so we're going to have u1 minus 2u2 plus v1. u1 minus 2u2 plus v1. And if we expand that, it's going to be m2 u1 minus 2m2 u2 plus m2 v1. Now, when we see this, we have basically what we're trying to find is an expression in terms of v1. We have two terms here, and here, that is in terms of v1 and others in terms of the constants. And so we're going to have the terms that has v1 in one side and the terms that does not have v1 in the other side. And so in the left side, we're going to have m2 v1 plus m1 v1, m2 v1 plus m1 v1, and that's going to be equal to our left side, which is going to be our right side. So m1 u1 minus m2 u1 plus 2m2 u2. Now here we can see that these terms, we could wrap it in terms of v1 and say m1 plus m2 is equal to all this. And here I'm just going to wrap this term here by u1 for convenience and say it's u1 of m1 minus m2 plus 2m2 u2. And so v1 is isolated here, so we could divide both equations by m1 plus m2 and get v1 is equal to u1 times m1 minus m2 plus 2m2 u2 over m1 plus m2. That's going to be our equation for v1. Now let's look at this over here. Now let's look at to validify whether this expression is correct. We're going to have to postulate an environment. Let's say we have a big ball here and a small ball here. The big ball has a greater velocity than the small ball. This is m1, this is u1, this is u2, this is m2. What would happen after the collision? It's clear that v1 is going to be, there's not going to be a big change in u1. In the final, in u1, when u1 becomes v1, the difference between u1 and v1 is going to be really small, because this has such a small momentum that its effect on the velocity of this ball will be very small. And also it has a small velocity. And so we are saying that m1 is bigger than m2 and u1 is bigger than u2. Then when we look at this equation here, m1 minus m2 is going to be a very large number, because m1 is large and m2 is small. m1 minus m2 is a large number, and it will be the difference between m1 minus m2 and m1 plus m2 will be really small. And so this expression as a whole will be very, very similar to u1. Also because m2 u2 is a small number, m1 minus the difference between m1 m2 and m1 plus m2 is very small. This term here is going to be very similar to 1, and this here will be very close to 0. And so it's basically a number that is very similar to u1. And so by looking at this, by postulating this environment, we could say that this expression is correct. Now, we're going to do the same thing for v2 in order to find an expression for v2. And we're going to do a very similar thing. Here, we're going to look at this expression again. And now, instead of substituting v2 by an expression in terms of v1, we're going to substitute v1 in terms of we're going to find an equation for v2, which is basically this here. So we're going to find an expression that gives v1 in terms of v2. And we can see that v1 is equal to v2 plus u2 minus u1 from this equation over here. Now then we can do the same thing. We have v2. We're trying to find what v2 is, and we have, again, we plug it into this equation, but now we're plugging in v1 with this number here over here. So we have m1 times u1 minus v1, so u1 minus v2 minus u2 plus u1, and so we have two u1s minus v2 minus u2, and then we're going to have, that's going to be equal to m2 v2 minus m2 u2. And then if we expand all that, we're going to have 2m1 u1 minus m1 v2 minus m1 u2 is equal to all that. And then again, find the terms that has v2 in. We have two terms in terms of v2 and three that are not in terms of v2. And so we're going to rearrange the equation. So we have m1 v2 plus m2 v2, so m1 plus m2 of v2, that's going to be equal to 2m1 u1 minus m1 u2 minus m2 u2, so minus m1 plus m2 of u2, because that's, when we expand that, it's minus m1 u2. No, that's going to be a minus, because we're going to need a plus m2 u2. We're going to have a minus and a minus to get a plus m2 u2 in one side. Alright, so now we do the same thing. We have v2, divide both sides by m1 plus m2. We're going to get 2m1 u1 minus m1 minus m2 times u2 of m1 plus m2. So this is our first, this is a term for v1 that's given by all these constants, and this is a term for v2. This is basically how the u1s and u2s change after the collision occurs between these two balls. And so we have this equation over here, this equation over here, and also we know that the velocity here, when contact with ground, u1 becomes, v1 is equal to minus u1 and v2 is equal to minus u2. We have, with these three principles, we're going to now move on to coding and simulating, with MATLAB, simulating a freefall collision system, or freefall elastic collision system. And so